Hey there, and welcome to your first lecture video for 1.1. This is week one. This video and the next video are going to be on 3D coordinate systems. So look for the corresponding section in your book, whichever version you're using, and follow along or read that and then watch this video. So the terms that we'll be covering are coordinate axes, right-hand rule, coordinate planes, octants, coordinates, projections, and 3D rectangular coordinate systems. All of these are things that you should know at the end of this video or after you've done the homeworks. And over here, we have the formulas that we'll be using in this section. So we have the distance between 2 points. I use P1 and P2 to represent the ordered triples here for convenience when I write them down here. And inside we have x1, x2, and x1, y1, and z1, and x2, y2, and z2 as the coordinates. So you probably have sort of an intuitive understanding of how this works, but I'm just trying to make sure that everything is described for you. And the distance formula right here, this is like the distance formula in 2 dimensions, but you add in this extra term with the difference of the z coordinates. I also sometimes will call these differences delta x, delta y, and delta z, just like you've seen in Calc 1 or 2 for representing differences of coordinates. And this formula gives you then the distance between 2 points in 3D space. The other equation is the standard equation of a sphere in 3D space. This is a hollow sphere, by the way, so it does not include points on the inside, just on the boundary. If you want points on the inside, then you need an inequality here instead of an equality. So a sphere is given by a center and a radius. It can also be given by 4 different points in space, and it can be given by a diameter and a center, I believe. So lots of things like that. But here's the equation of a sphere. And it looks a lot like the equation for the distance between 2 points because it is. It's just when the distance is constant and you've fixed a single point, let's say P2 in here. So A, B, and C are fixed, R is constant, and then you bring the square root to the other side and you get the formula for the equation of a sphere in standard form. All right, last is these objectives here, and then we'll go over the terms. So we have 3 different difficulties of objectives, easy, medium, and hard, and we'll go through them one at a time. So for the easy objectives, I want you to understand 3-dimensional coordinate systems intuitively. So this just means, if someone asks you, hey, what's a 3-dimensional coordinate system? You should be able to briefly describe it to them, give them maybe a picture and say, yeah, I kind of understand. It like represents how you move things around in space and blah, blah, blah. It's a model for things. So nothing particularly fancy about that. Just know what this thing is. The second easy objective is that you should be able to draw points that are listed using their coordinates in XYZ space. So take something like this and translate it into a picture. And you should be able to visualize that process in your mind. I do want to emphasize that a lot of first one is that we want to be able to calculate distances between points. So that is just using that first formula in the formula section. XYZ space, R3 here. R3 is just another way of saying XYZ space. It's just a mathematical way of writing it. If I go like this, that. Second objective here, in the medium section, is to recognize simple equations for basic geometric objects in R3. So this is things like spheres or cylinders or planes, lines, anything like this. You should be able to recognize when an equation represents one of those things. And similarly, object, you should be able to write out an equation. Last medium objective here is that you should be able to, again, draw points, lines, and planes, but this time in non-standard coordinate systems. So by non-standard here, I just mean a coordinate system where the x, y, and z axes might be labeled differently. So maybe where the x is, or where the x normally is, you put a z, and then where the negative z is, you put an x, and then where the negative y is, you put positive y. So that would be an inverted coordinate system and sort of rotate it around, but I want you to be able to draw points there regardless. So even if coordinates are all shifted around and swapped, you should still be able to follow the axes and figure out where, 3, 7, minus 4 is in that coordinate system. Can you do that? All right, last but not least is the hard ones. These are not objectives that I expect you to have done by the end of a section or even by the end of a week. These are objectives that are, if you're trying to make sure that you really, really understand the section. Once you get these, you can consider that section pretty much mastered. So you should be able to rotate coordinate systems mentally and swap the axes mentally. So in your mind, you should be able to see X, Y, Z axes and sort of rotate them around continuously, or swap the X and the Z, put the positive axes where the negative axes are, do that all in your head and draw things in there. The second objective here is that if somebody describes something to you using natural language, it's a half sphere centered at 1, 1, 1 of radius 4 with a cone scooped out of the center of a given height, you should be able to write down some equations or inequalities that correspond to those shapes. Last is that you should be able to compute distances between objects. So distances between lines, planes, spheres, and cylinders. Now that is actually a tricky process. It could involve some calculus, and we might deal with that stuff later on. But this is one very, very hard goal for you to work towards. All right, so that is all of our objectives, and now we'll go over the terms and what they actually mean. So let me zoom in here. So first up is our coordinate axes. So these are lines that make up a coordinate system. And I have a picture drawn over here of them for you. You've got the positive and negative x-axis, positive and negative y-axis, positive and negative z-axis. And they meet here at the middle in the origin 0, 0, 0. Notice that the positive x, y, and z axes are oriented in a particular way. If I were to swap the x and y, that would be non-standard. So they go x, counterclockwise to y, counterclockwise to z, then counterclockwise to x. That is our standard coordinate system. And there's a way of remembering that using the right-hand rule. So this is a way to remember how you're supposed to label things in standard form. I drew a nice little picture over here for you. So you take your hand and you hold it out in this way with your index finger pointing out, your middle finger pointing perpendicular to that, and then your thumb pointing perpendicular to both of those. So you might have seen this if you've taken physics or something. But your index finger is meant to represent the x-axis, middle the y-axis, thumb the z-axis. And this is one way that you can always remember, oh, that's how a 3D coordinate system is supposed to look, if you forget. All right, next up is our coordinate planes. So these are, you choose two axes here, maybe the x and the y. We're familiar with coordinate planes in the sense of the xy plane, but now we have 3 variables and 3 axes, so there can be different planes. And I have pictures of those over here. So the standard coordinate planes are the xy, which is this flat one, and the z sticks out from that. The yz, which is sort of head on, and the x sticks out from that one. And the zx, sometimes xz, which is sort of sideways to us, and the y sticks out from that. So The pattern is, all right, whatever variables make up the plane, the other variable sticks out from it. And those are our coordinate planes. Now, the coordinate planes divide XYZ space into 8 sections, and these chunks are called octants here because there are 8 of them, and they're separated by the coordinate plane. So here I've drawn the first octant. So here you've got your X, Y, and Z axes, and this whole space that the positive ones occupy is the first octant. And just like there are quadrants for the XY plane, and they're labeled in a specific way, you've got the first octant here, and then if you go back this way, you've got the second octant behind it. Next to that's the third, and then the fourth in front of that. And then you start over underneath, and here you've got the 5th, 6th, 7th, and 8th octant. There are 8 of them. All right, next up we have coordinates. You know what coordinates are, but I have to tell you what they are in 3 dimensions just to be clear. They are an ordered list of 3 real numbers used to encode a position in XYZ space. And we write those coordinates using parentheses and commas. So 1, 2, 3, first position, second, third. Now visually, you can think of that as walk along X, then Y, then Z, and you get to the position you want to be at. All right, then we have projections. Projections are exactly what you think they are. They're just projections, like in like if you're watching a movie on a projector, they take some image and put it somewhere else onto a flat plane usually. But in math, we can be a little more specific than that. We say that a projection is a unique point Q in a chosen coordinate plane so that the line to the point you're looking at is perpendicular to that plane. And here's a picture of that because that's probably a little confusing. So if I were to take some point, let's draw it in white here on the sphere. Let's say we draw this one right on the edge. So this is our P, and we were to project it, we would probably get this point Q over here so that the line from P to Q is at right angles to the XZ plane. All right, so if you look at some other point here, like Q prime or something, then this line is not at right angles to the XZ plane. And so that would not be the projection. Technically, this is called the orthogonal projection, but that's not super important for us, and you'll learn more about it if you take linear algebra. You can also project onto other planes that are not the standard XYZ ones, but that is much more difficult. And again, you won't want to take linear algebra to learn about that. All right, last term to define here is the 3D rectangular coordinate system, and that is just everything that we just talked about all together. So you've got your axes here. That's the laser point. You've got your axes here, X, Y, and Z. You've got your planes. You've got objects that you can draw in them, points that you can specify on each one, and then projections and all that stuff, your octants and whatever. All of that together gives you your 3D rectangular coordinate system. And it's called rectangular because there are other coordinate systems that are based on circles and rotations and that sort of stuff. But okay, so that is the end of this video. And just remember, you'll use these formulas for all of the problems. And in the next video, I will go over some examples. We'll work them out for you of problems that you might see in the homework. All right.